So today I will talk a little bit about, some of the work that we're doing sort of beyond joint replacement, the total joint replacement that you hear about. I was hoping to benefit from Dr. Laurencin's introduction to tissue engineering, but I will talk a little more about some of the work that we are working on. So this is tissue engineering has sort of captured the public imagination because it's actually a really, really simple concept, like many great ideas. So what you do is that you take the patient's own cells, you provide what we, in some cases, a scaffold system, a scaffold that's designed to mimic the extracellular matrix, and voila, you have tissue. Okay? Of course, devil is in the details. How do you engineer that tissue that's actually functional and that's actually physiologically relevant? It's something that we're working on. So tissue engineering is a relatively new field. For the past 3 decades, what we have been doing, that we have been working on optimizing this methodology I talked about, taking the patient's cell or taking cells, putting on a scaffold system, and engineering functional tissues. So as the field advances, what happens is that we're beginning to think about assembly of different type of tissues. And this means that connecting different type of tissues together to form complex tissue systems that are multi-tissue and more organ-like or more physiologically relevant. And to do so, understanding the interface between different type of tissues is a very critical juncture, almost really a threshold before we can move to engineering complex tissue systems. And this is being recognized by the field. So now this importance of connecting different tissues together is much more relevant actually in the musculoskeletal system. As you know, some of the major challenges aside from, from bone regeneration is really the regeneration of soft tissues, such as cartilage, articular cartilage, which lines the surface of joints, ligaments, which connect bone to bone, and muscles, which connect, tendons, which connect muscle to bone. And current grafting systems are biologically based soft tissue graft systems. And what really difficult with these systems is that their long-term outcome sometimes is mixed because the lack of integration between the existing grafting system with bone. So the research question that we're really interested in our laboratory is how do you achieve biological fixation of soft tissue grafts of bone, whether it's biologically derived grafts or tissue engineered grafting systems. And I think the analogy that I want to make is how do you connect a rope to the wall without using fixation pins or screws or any sort of mechanical devices? That's basically what surgeons do nowadays. They take soft tissue grafts, they use pins, they use fixation devices, metallic screws, or degradable polymer screws, but they use something to connect that to the wall, which is bone in this case. So as you can see, there's some examples of systems. This is the shoulder, which is the muscle. This is the bone, the tendon, the supraspinatus tendon. And here is the anterior cruciate ligament, which connects the femur to the tibia. And also the osteochondral interface, which connects cartilage to bone. And this is actually a very, very small transition. In humans, you're looking at about 100 microns. At 100 microns, actually extremely complex, as you can see here in some of the schematics, and also in some of the histologies that you see here, which is actually ligaments connect to bone through a whole different type of tissue. And this little small piece of tissue, or small transition, is further divided into 2 regions. One is non-calcified and one's calcified. So why such complexity? In nature, complexity is not accidental. So this complexity is important for a variety of reasons because this way results in a gradient of cellular, chemical, and biological properties, and especially mechanical properties, that allows you to first transit from soft tissue to hard tissue. Soft tissue that primarily sustains tension to something that primarily sustains compression, such as bone, and also that to minimize the formation of stress concentrations. So you can go from soft to semi-hard, then to hard tissue. So the deformation is not sudden, so failure is limited. So consequently, this interface is extremely critical when you're trying to connect different type of tissues together to assemble, let's say, a total joint. So given these motivations, the work that we have been working on also in the field by many researchers, it follows a couple areas. First, you look at the interface itself. So exactly how does nature connect a rope to the wall, in this case, a ligament or a tendon, to bone? And also that to understand the fact that you're connecting different types of tissues together, so different cell populations, they had to work together in order to engineer or repair that transition that's lost. And these informations fit into what we call biomimetic scaffold design, the scaffold system that ultimately will allow you to integrate soft tissue with bone. And like all tissue engineered systems, this is evaluated in vitro and also in vivo and optimized based on these results. So for today, in the interest of time, I'll talk about some of the work that we've done in terms of in the anterior cruciate ligament system and the ACL, which is also the most commonly injured ligament of the knee. And fixation of the ACL graft is a significant problem. So one of the first studies that we looked at was really looking at the postnatal remodeling of the insertion site. So how does the insertion change? This also has specific relevance for ACL patients because the demographics is between 15 to 35-year-olds. So you have people who are skeletally immature, who are still growing, and the patients who are skeletally mature. So you see that the interface is different as a function of age. So as a tissue engineer, when you're trying to design interface, you have to think about the patient. What is the patient demographic that you're working with? So this was very illuminating to us about what type of interface, what type of organization we should engineer on our scaffold systems. And we also looked at what is the mechanical properties? You know, if I'm trying to design something, I need to be able to know how strong something is or how strong should I select the material to be. So we looked at the mechanical property across, this is a very difficult crossing of 100 micron range, and looking at the non-calcified versus the calcified regions. So these are important information that allow us to design our scaffolds to make it biomimetic. Now, in addition to looking at, what are the biomimetic design properties, looking at the interface itself, we also have to think about, working with biologists, we have to elucidate the mechanism of repair. So how does the interface repair? Currently, that is not known. So there's a lot of work that's going into this area. So one of the hypotheses is that when you put a piece of ligament or a piece of soft tissue next to a hard tissue, what we found, clinical observation, that sometime over time, a wall builds between them. So how does that wall get built? Okay? So some of the hypotheses that were formulated is that the interactions between the cells from the soft tissue and the cells from the bone tissue, their communication is critical for initiating the repair response. And more importantly, their communication is important in inducing the differentiation of stem cells, who actually are ultimately the ones who are repairing the interface itself. So through a series of co-culture and tri-culture model systems, we elucidate some of the mechanism underlying interface regeneration in terms of how do the cells have to interact with each other so that you can actually regenerate the interface between soft tissue and hard tissue. So the cell-to-cell communications through pericranial factors as well as cell-cell physical contact have found to be extremely critical in connecting soft tissue to bone. So taking all this information together, how do you assemble that and actually designing a functional grafting system that can actually indeed connect different types of tissues together? So to bring this home, this is the characterization that shows the ligament, the interface, and the bone. And this is our scaffold system, which you have a ligament phase, you have an interface phase, and you have a bone phase. And 3 different types of cell populations are seated on phase A, phase B, and phase C. And they work together to regenerate a contiguous graft. So this is in vivo tracking of the 3 different cell populations over 28 days in vivo. You can see that the cells remain viable, and the 3 different types of cells are implanted. And over time, indeed, cells are the true tissue engineers, that they engineer 3 different types of tissue. And in this grafting system is a continuous scaffold that the soft tissue is seamlessly integrated with bone. Okay, so this is really what our end goal is in terms of engineering complex tissues, is to be able to connect a piece of soft tissue with a hard tissue by doing it in a biomimetic manner. Now, in terms of application of this system, we're envisioning using the system to, you can use this for a total ACL repair, okay, for a total ACL graft that actually can pre-engineer the interface. So you have the bone phase, you have the interface phase, and you have the ligament phase. So this is a total joint prosthesis, total ligament prosthesis that you have pre-engineered integration. And when you come to in vivo, you only have to worry about osseointegration of bone-to-bone integration. And another way that you can potentially utilize the scaffold system is actually to use them to induce interface formation on current ACL reconstruction grafts. And this can be done in a variety of ways, which I won't go into details here. But the idea is that to be able to design systems, grafting systems that will enable biological fixation in terms of connecting a rope to the wall without mechanical fixtures, and also through multi-tissue formation. I've given you an overview of some of the work we've done in the past 7 or 8 years on how to regenerate different types of tissues simultaneously. So what is next? Okay, what is it, from a patient perspective, what can you expect down the road? So what we're doing next is that if you think about it, what our work has illustrated that more than one cell type is necessary to engineer more than one type of tissue. But from a clinical perspective, from a translational perspective, that's extremely cumbersome. You cannot ask a patient to come in and donate 3 different types of cells and come back for the surgery one more time. Right? So we're designing what we call smart scaffold systems that allow you to really seed a single cell population, whether it's mesenchymal stem cells, adult stem cells, or iPS cells. And then the cells will be smart enough to know in phase A, they become ligament-like, they form ligament-like tissue. Phase B, they form the interface that allow it to connect to the phase C, which they form the bone-like tissue. So this is what we're working on towards sort of actually making this translational to the bench side. In addition to that, I think what this work would have sort of in the context is sort of the in the not so distant future. You heard questions about the total joint replacement. Yes, there's a lot of advancement that has been made in the total joint replacement, and NIAMS play a significant role in bringing that to fruition. However, total joint replacement, along with the increased number of implantations with these joint systems, there's also an increased number of revision surgeries. Okay? And that's because we are an aging and yet physically active population. And the demand that's placed on our body in an aging population is extremely significant. And there's cause for some concern for some of the total joint replacement systems. So these systems work very well within the confine of their design. However, they're not optimal. Okay? So by engineering complex tissues or thinking about how different types of tissues can be connected together, our goal is, if necessary, engineering total joint systems. And a lot of times when you can actually connect soft tissue to bone, you can actually negate, even potentially, the need for a total knee replacement, right? Because total knee replacements are performed because of cartilage damage. So if you can actually attach cartilage to bone in a functional manner, you don't have to get a total knee replacement. Okay, total hip is a whole different story. But some things like this that you can by understanding how different types of tissues together, you can moderate the type of clinical treatment, make them less aggressive, and also when necessary, you can make total joint regeneration that will allow you to be able to engineer a joint that's interconnected. Okay, and as far as the patient is concerned, at the end of the day, they should not have any synthetic material inside them. So that's really the goal or dream of tissue engineering, that you would have your own tissue that's actually grown by your own cells, but with a little bit of help from tissue engineered scaffold systems. So that is the dream for the future. So I want to acknowledge the brilliant contributions from the students who have actually performed all this work and that I've talked about here. And also the collaborators I've had, many collaborators who have had in bringing this work about, especially Scott Rodeo at Hospital for Special Surgery, who is our long-term collaborator on the ACL project, and also Adele Bosky, also at Hospital for Special Surgery, and Steve Doty, and who have helped us really to understand the interface and also characterizing some of the functional properties, as well as Fei Chen, who was at Columbia and later at NIAMS Intramural, who worked with us closely on the co-culture and tri-culture models to elucidate some of the mechanism governing cell-to-cell interactions and its relevance for multi-tissue regeneration. And also that I want to acknowledge my mentors who, we stand on the shoulders of giants. In terms of interface tissue engineering complex tissues, we really are building on all the knowledge base that has been gathered in the past 3 decades in tissue engineering. And I want to acknowledge my mentors, Sal Pollack and Paul Duchenne at the University of Pennsylvania, where I did all my undergraduate and graduate training. They taught me how to become academicians. And also my postdoctoral mentors, Dr. Cato Laurencin and also Dr. David Kaplan. at Tufts University, working with Dr. Laurencin, who actually really stimulated my interest in tissue engineering. I was not a tissue engineer before I started my postdoc. And also that I think working with him, one thing that was very valuable I learned is to work with clinicians. How do you work in an interdisciplinary team? Because by working with clinicians in tissue engineering, you can actually understand how you can better translate your technology, a scaffold design, to something that can actually go into a patient. I also want to acknowledge the support from NIH NIAMS for funding our work. And also, when I first started as an assistant professor at Columbia, my first year I applied for 10 proposals. I wrote 10 proposals. And the last one got funded. And most of my proposals that I applied for were NIH proposals. And the one that funded was not an NIH proposal, it was a Whitaker proposal. So, it was very, very depressing. But I think what was really helpful to me is that, I had the guts to call NIH and find out, what should I do? And not like the DMV, so that, because I had a view that this experience is, my grants proposals went into a black box, they got chewed up and spit back at me. So that's how I felt at end of the first year. But no, I think I have to thank all the NIAMS staff and all the NIH CSR who really helped me understand the grant process and also writing a better proposal. And I also want to acknowledge the ORS Women's Forum, which really, I think, helped mentor a lot of female scientists. And this is also where I met Dr. Joan McGowan. And I think they really served as a role model for us, for young investigators, so that we don't have, because when someone asks me, do you have any horror stories to tell as a woman in science? No, I don't. Actually, I'm very fortunate, and I think it's thanks to all the mentoring that I have received, being fortunate enough to receive in my career. Finally, I want to thank the funding resources for supporting this work. And also that to say happy birthday, NIAMS, and a special hello from Columbia BME department. We have only 18 full-time faculty members, but the 8 of us are funded by NIAMS. So we want to especially thank you for supporting us and also to congratulate you on this auspicious occasion.